A free body diagram is a graphical depiction of our object, and it shows every force acting on that object. So here we have a block sitting at rest. Person A is pushing on it, trying to get it to move to the right. Person B is pulling on a rope that's attached to the box, trying to get it to move to the right. But the box is just sitting there. So I'd like you to draw a free body diagram for the block. Here's our block. And I like to go around thinking about what's touching the block, because almost every force we deal with right now requires contact. You push on something, you go on, you push on it, there's contact there, you can exert a force on that object. Almost everything requires contact. There's one force in mechanics that does not require contact, and that's the force of gravity. The force of gravity can reach in at a distance and exert a force on something. Everything else, there has to be contact for that interaction to take place. Next quarter, when you take electricity and magnetism, you'll learn that the electric force also interacts at a distance. Two charged objects can exert forces on each other without touching each other. But for physics 4a, for mechanics, every force requires contact except for one, and that's gravity. A good starting point is looking at everything that's touching our object. Person A is touching our object. Person A is exerting a force on our box to the right. It's the force from A on our block. The rope is touching our box. That's pulling to the right. The force, the rope on the box. The ground is touching the box. When surfaces interact, we say they can interact two ways, through a normal force and through a friction force. The normal force perpendicular to the surface, the friction force parallel to the surface. So there's a force from the ground acting on the block in this direction. There's a force from the ground on the box in this direction. That's from the friction interaction with the ground. That's everything that's touching our block. What can reach in from a distance? Gravity. Gravity points toward the center of the earth. That's the force from the earth on the box. If you look at this free body diagram, it immediately is not that helpful. All you see is force, 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 force. It's not really helping you to spot what's going on. For common forces, it's a good idea to use a special symbol. So when you look at it, you immediately know what the force represents. Some common forces are the normal force. So oftentimes we'll just use a capital N instead of indicating Fg on B, force from the ground on the box. We would just put an N there, and then you would know it's a normal force, capital N. Another common one is tension from a string or a rope. Friction is another common one. We typically use a lowercase f. And the force of gravity is a common one. So you can use F sub g, or a lot of people like to use W for weight, because what is the force of gravity? It's the weight of the object, right? I try not to use W because we have a lot of W's in physics. We use W for work. We use W for the units for power, right? The watt. And so W pops up in a number of different places. So I'll try to use F sub g. But a common one you see, people like to use W for the force of gravity. And then you can just use F, capital F, for any remaining force that pops up. Now I'm going to redraw my free body diagram And I think you'll see that this becomes more clear when I use the other symbols that represent the normal force, the tension in the rope, the friction force, etc. We've got the force from person A pushing on the block. We've got the tension in the rope pulling on the block. The ground pushes up with a normal force on the block. The ground is pushing back to the left through friction. And gravity is reaching in. That's the force of gravity. That's the earth acting on the block. Sometimes when you're first starting out, it's a good idea to use these subscripts like this. It helps you figure out exactly what the force is coming from, what the interaction is that's providing that force. But once you've done that for a little while and gotten used to the subscripts, you really don't need them anymore. Where I use subscripts is to differentiate when I have different masses in my system or different tensions in my system. I don't want to have a F sub G on one free body diagram and the same symbol F sub G on the other free body diagram if those two forces are different. If they're different, they have to be different symbols. So I would put an F sub G1 and an F sub G2, something like that, some different subscript so I know they're different. But we'll deal with that when we get a more complicated free body diagram. For now, we have every force acting on the block represented in this free body diagram. I think we should do a quick example where we have to keep track of subscripts. In this case, we're pulling on box 2. Box 2 is connected to box 1 with a rope. So both boxes are moving along to the right, and there's friction between the boxes and the ground. So let's draw free body diagrams for box 1 and box 2. Starting with box 1, what's touching it? Well, the rope is touching it. That's tension in the rope pulling on box 1. The ground is touching it. That can interact two ways, through a normal force and through a friction force. And the friction force is going to be to the left. And what can reach in from a distance? Gravity. Now, if you haven't done it already, do your free body diagram for block 2. Again, I like to think about what's touching it. The pulling force to the right. We're pulling on something. There's a rope attached to block 2 that's also attached to block 1 that's pulling it back in the other direction. Tension in that rope. The surface is touching it through a normal force and through a friction force. And what can reach in from a distance? Gravity. Now let's take a look at these two free body diagrams. When I look at this, I see I have a normal force and a normal force. But those two normal forces are probably going to be different. I can't call them both the same thing if they're different. So I'm going to call this one N1, the normal force on box 1, and this one N2, the normal force on box 2. I've got two friction forces. Those two friction forces are probably different. I'll call this one F1 and this one F2. I've got two forces of gravity, the weight of the object. And if the masses are different, those have to be different. I'll call this 1, which is going to be its mass times g. And we'll call this one 2, which is going to be its mass times the acceleration of gravity. I only have one pulling force, so I'll just leave that the way it is. There's no ambiguity with that. I have two tension forces, but the tension is the same from both. The tension in a rope is the same everywhere if the rope is massless. So the tension that the rope is pulling on box 1 is equal to the tension that the rope is pulling on box 2. These two are the same. So I'm just going to leave them both as T. I don't need a T1 and a T2 if they're the same. I'll just leave them both with the same symbol. That tells me they're the same. So if you have two symbols that are the same, like I do here, they better be the same. And if you have two items that are different, like two different mass boxes, you better indicate somewhere that they're different with subscripts or some other method. Don't have two symbols that are the same if the forces that they represent are not the same magnitude.